Like, yeah,
Okay, so they control it.
welcome everybody. Is that my fault? Oh, good. Thank you very much. Good start. Welcome everybody to this evening of physics. This is a public event that's co-organized with DAISY and the DPG, the German Physical Society, as part of a workshop that's been going on here since Wednesday and continues tomorrow, where a bunch of particle physicists are getting together to discuss what may be one of the next machines that we want to construct, which is an electron-positron collider at high energies, which we call a Higgs electroweak top factory. And this is a public event associated with that. The event is being live streamed on YouTube and it's a Zoom webinar, so hello everyone out there. And it will be recorded, so you hopefully all know that in advance. So I said the words Higgs electroweak top factory, which is a kind of particle physics jargon that will drive everyone mad. Luckily, to explain what that actually means, we have here with us Professor Hitoshi Murayama, who's a Japanese-American theoretical physicist and cosmologist. He's a professor at the Center for Theoretical Physics of the University of California, Berkeley, and the director of the Kavli Institute for Physics and Mathematics of the Universe at the University of Tokyo. And he's going to take us over the next 40 minutes through the background and content of what we're discussing in this workshop. After that, there'll be a chance to ask him some direct questions, and then we're going to have a panel discussion with some of my eminent colleagues, where there'll be a chance for people in the room to ask questions, and also we'll be taking questions from the online audience as well. But now, without further ado, Hitoshi, over to you.
Hey, thank you, John. Guten Abend, meine Damen und Herren. Das ist alles, was ich auf Deutsch sagen kann. Entschuldigung. Okay, so my title today is the Higgs boson, particle superhero and tour guide to new particles. And of course, you have no idea what I mean by this. Hopefully, you know what I mean by this by the end of the talk. So what physicists do is actually something very simple. We look up the night sky just like a little kid and start wondering some deep but simple questions, like how did the universe begin? What is its fate? What it's made of? What are its basic laws? Why do we exist? Where do we come from? And the story today really has to do a lot with this question, why do we exist? This kind of question used to be part of the philosophy maybe, but this has really become a scientific question these days, and that's something we would like to advance by talking about yet another collider experiments in particle physics. I'm sure everybody heard of this idea that the universe started with the Big Bang 13.8 billion years ago. So we all came from here, the Big Bang. But the question now is, well, what exactly happened since? And what led to our existence today? And that's the kind of question we'd like to talk about. The Big Bang is not just a story, because this really happened 13.8 billion years ago. So if you work really hard to look 13.8 billion light years away from us, you see the Big Bang. Oh, Big Bang is happening right now. You see that way, you see the Big Bang. You look that way, you see the Big Bang. You can actually take a picture of the Big Bang. And this is the best version we got so far, using the satellite called Planck satellite from European Space Agency. And this is the picture of the Big Bang. You can actually see it in front of you. This picture is actually extremely exaggerated though. So you see some hot spots in orange, some cold spots in blue, but the difference between cold and hot is very, very tiny, only at the level of 1 part in 100,000. So this is actually a very boring, bland picture, and that's the way Big Bang was. So starting from this Big Bang, how did we come to exist today? And how did we survive the Big Bang? And that's the kind of questions we'd like to understand. So one thing we know, and everybody here knows, is that we are all made of atoms, right? And one thing we have learned the last several decades is the fact that only hydrogen and helium were made in the Big Bang. But for your body, you need calcium for your bone, iron for blood, you need to breathe the oxygen. Where do they came from? It turned out that they were actually made in stars. So this is something we have learned rather recently. So Big Bang made hydrogen and helium. First stars were made of hydrogen and helium only. But what stars do is to build atoms. They build more chemical elements at their centers. And some of the stars, the heavy ones, would explode at the end of life, and elements they have built get dispersed into empty space, and they eventually become dust. And that dust gets together again by the force of gravity and build a child star. And that child star also starts building chemical elements all the way up to iron. Again, they explode and disperse all the atoms they made into empty space again. That becomes dust. Our sun is believed to be a grandson of the first stars. So when our sun was started to build up, then there was a dust made of elements like oxygen and calcium and iron already in the dust that eventually hit each other, stuck with each other, developed to build a rock, and that's our planet. So that's how we came to exist. So out of these explosions came all the elements we need. This is my kits. And so you are all actually stardust. So that's something we have learned. But how do we know that stars actually make elements? Nobody has seen that, right? Because that's happening at the core of the stars. Stars are so dense and hot gas, you can't see through it. You can never see what's going on at the center of the sun. So we thought. But at the center of the sun, something like this should be happening, building helium out of hydrogen. And when this reaction happens, before the reaction, it's heavy, and after the reaction, it's light. Mass is lost, and amount of mass lost converts to energy by Einstein's famous equation, E equals mc squared. That's how the sun shines. So as we speak, the sun is getting whopping 4 million tons lighter every second because it's turning mass into energy. But how do we know that? Well, particle physicists came up with this brilliant idea that there is actually byproduct in this reaction. Some of them are called antimatter, in this case, antimatter of electron called positron. Some others are called neutrinos. They are so shy particles, so they can get out of the sun without any problems at all. So what that means is that if you actually manage to catch those neutrinos, you can look into the center of the sun. And that's what my friends in Japan have done by building this huge water tank called Super Kamiokande. And they even managed to take a picture of the center of the sun using neutrinos. So these reactions are really happening. Stars are factories of building more atoms at their cores. And for this reaction to take place, there's some strange force called the weak force we don't often hear about. And that weak force is really essential for this reaction to happen so that you can build up heavier elements so that eventually we come to exist. The nature of the weak force has been a mystery for many, many decades. But one collider experiment at CERN called LEP, LEP stands for Large Electron Positron Collider, very creative name. And that experiment studied this nature of the weak force in great precision, and now we think we understand it very well. After all, this strange weak force is exactly the same kind as something we're familiar with based on electricity and magnetism, except for the fact that it doesn't go very far. It goes over only a billionth of the size of an atom. It's very short-ranged, which is actually a good thing. If the weak force were longer ranged, then our entire universe becomes so radioactive that we wouldn't be able to live. On the other hand, if the weak force was much shorter ranged, then this reaction wouldn't happen, then sun wouldn't shine, we wouldn't exist either. Somehow, it has to be done just right. And that's something we still don't understand, why weak force goes over the range, which is just right for us to exist. And to understand this mystery, we actually listened to our colleagues in physics called condensed matter physicists who studied this phenomenon called superconductivity in the laboratory. And they have very special property. We all know the magnetism travels over long distance. If you hold a compass in your hand, that will point to the North Pole, because the North Pole is pulling the needle of your compass over thousands of kilometers. So magnetism goes over long range. But what they discovered is that in a piece of material called superconductor that loses electrical resistance, magnetic force becomes short range. What is supposed to be long ranged somehow managed to become short ranged because there are so many electrons inside the material that would disturb the magnetism so that it can't go very far. That's what they discovered. So we learned from them. So we would like to apply the same idea to our entire universe. By the way, this kind of a superconductivity is something we are now using to build a maglev, an incredibly fast train in Japan. It's very fast. It can go fast because it actually levitates. It's floating in the air by the force of this magnetism I talked about. Otherwise, it would shake too much that it wouldn't feel comfortable on that kind of train. So borrowing the idea from our friends condensed matter physicists, we believe our universe is filled with a particle called the Higgs boson. Somehow, this particle Higgs boson was everywhere early on in the universe, but at some point, the universe became cold enough that the Higgs boson froze into empty space. So it's all right here, packed very densely. And what's going on here is that when weak force wants to act on somebody, then it gets so much disturbed by this Higgs boson stuck in the universe today, and that's why it can't go very far. That's why stars would shine at exactly the right rate so that we can exist. What it also means, though, is that the particles like electron also don't go very far because they are disturbed by the Higgs boson as well, which is a good thing. Because if this Higgs boson is not there, what happens is that electrons inside any atoms will start moving with the speed of light and instantly disappear. And you can see I'm old enough to have a picture with Einstein in color, which is hard to believe, but anyway. And so what happens here is that we all evaporate in a nanosecond too. So Higgs boson is the thing that keeps you together. That's why I'm calling it the superhero. And I actually spent 5 hours last night trying to paint this emblem from S to H. And I don't know if I'm very successful in that. But anyway, he is the superhero. But we only discovered it like 10 years ago. We haven't gotten to know him very well. So there are still lots of questions we have about him. Who is he? Well, you might say that's Clark Kent, but that's not the answer I'm trying to get. So what exactly is the Higgs boson? We still don't know. Why is he frozen in empty space? What happened to it? We don't know. And that all relates to this question, why do we exist? So we gotta find out. So one thing we do know, though, is that you have seen this picture of the Big Bang, but it's actually not the Big Bang itself. Universe started out over here, but the picture of the Big Bang I showed you is only up here, when the universe was already 380,000 years old. Of course, compared to 13.8 billion years of the life of the universe, that's still a very, very young baby universe. That's amazing. We managed to take a picture of the baby universe, but it's still not the Big Bang. For the same reason, we can't see the center of the sun. Universe is also filled with gas. When you go back in time, universe becomes smaller and hotter and denser. At some point, light can't get through it anymore. So all you can see is the surface of the Big Bang. Just like what we can see is only the surface of the sun, not the center of the sun, unless your eyes can see neutrinos. Can any of you see neutrinos? No? When I ask this question in Berkeley, always a couple of students raise their hand. and I recommend them to go to hospital right away. So, no matter how hard you try, what you can see with any kind of telescopes, only up to this point. You can never see beyond that. But we also know that Higgs boson apparently flows into empty space around here. So how do we study that? The only facility and experiments that can study this is by building what is called the collider experiments. You smash particles against the particles at an incredible energy that would sort of redo the Big Bang. Well, of course, if you really redo the Big Bang, the universe will be born. I don't think we can do that. But we might do a little bang, and that's the idea of an experiment, collider experiments. So that's one thing we really would like to do so that we can understand why we exist, thanks to the superhero of the Higgs boson. There's yet another mystery. So this picture made a big news on newspapers and media and TV. This is the first picture reported by the new space telescope called James Webb Telescope. And this is a picture of distant galaxies, again, billions of light years away from us. But one thing you would notice right away is that there's some strange object in this picture. Galaxies are supposed to be round, maybe sometimes a little elliptical, but you don't expect to see something this much stretched out. But you see many of these things. This one is also very stretched out. That one is too. That one is too. How could there be such a strange shaped galaxies? It turns out that this also has to do with the question, why do we exist? So this is a picture of what is called cluster of galaxies, because there's some hundreds of galaxies living together in here, and that is what is called a cluster. And in a cluster of galaxies, there is a mysterious material called dark matter that is actually binding these galaxies together by the gravitational pull. So there's a lot of dark matter in the cluster of galaxies where the gravity is strong. And if you are sitting on a planet and looking at a very distant galaxy that happens to be beyond this cluster of galaxies, then the light coming from this faraway galaxy would fall by the gravitational pull from dark matter, so it bends. So cluster of galaxies then act as if it's a magnifying glass. It bends light. And if we have an experience looking at a magnifying glass, trying to read something, but on the edge of the magnifying glass, maybe letters get so distorted that you can't read them. So it's sort of like that. The image of galaxy far away got so much distorted because the light bends on its way by the trick performed on you by the dark matter. Just to get an idea how that works, imagine that you have a bunch of galaxies in the background flowing like a river, and only when one galaxy comes sort of right behind this cluster of galaxies, it shows this really, really stretched out image. So you can see that. So you see these stretched out images, but once they pass behind this cluster of galaxies, they go back to the normal shape because nothing is happening to them. They are at a totally different location. Those galaxies are really far away. Dark matter is in front of them, but that dark matter is playing tricks on us. That's why they get so stretched out. So dark matter is something we don't understand either, but they do exist. And that's important to us. I told you already that the universe started very, very bland. So this temperature variation is really, really tiny, only at the level of 1 part in 100,000. But when it's a little hot, there's a little more dark matter, and they pull more dark matter by the force of gravity. Then there's a little bit more dark matter there. Then gravity is a little stronger. It pulls more stuff in there. Then this more dense, stronger gravity pulls even more. And then it starts to build up this kind of contrast. And when dark matter pulls in the ordinary gas made of oxygen and hydrogen, they start with interaction with each other. They emit light that could cool them down. Then eventually they collapse and start forming stars and galaxies. And so this is how stars were made. On the other hand, in a computer simulation, you can study wrong universe that doesn't have dark matter in it. Then 13.8 billion years later, nothing. No stars, no galaxies, no us. So I regard dark matter to be our mom who nurtured the ordinary gas came from Big Bang and assembled them into a fully grown stars and galaxies. So that's also very important for the question why we exist. As a matter of fact, most of the stuff in the universe is not what we know. Only 5% of the universe is made of atoms. The remaining 95% is something totally different, and we don't know what they are. And dark matter, as I said, is very important for us to be born, but we haven't met her yet. So I really would like to meet her at some point and say thank you, but I haven't managed to do that yet. So how do we study these questions using particle accelerators? So Enrico Fermi is a famous physicist, he's also a Nobel laureate, who came up with the idea how we might be able to study the Higgs boson in the laboratory. And the idea he came up with is a particle accelerator of this size called Globatron. It turns out that with the idea of the accelerator back then, it really needed to be this big to reach the energy to be able to produce the Higgs boson. Since then, everybody worked very hard. We managed to squeeze this Globatron into the Large Hadron Collider, which is 27 kilometers in circumference near the Swiss-French border. It is still big, comparable to the runways of Geneva Airport. That's 100 meters underground, so you're not supposed to be able to see them from aerial photograph. But in this big circle, we let the protons, the tiny particles, go round and round like a hammer throw. And you also do it in the opposite direction, and so you smash them against each other, and that's the little bang. That's how we would like to know how the universe was like when the Higgs boson froze into empty space so that we could live today. And this is a difficult experiment. You need to fill this underground tunnel by a large number of high-tech equipments. And so in this blue object, the protons are running at nearly speed of light in two opposite directions, and they would meet and do some reaction at a couple points along this big circle. One of them is called CMS detector. And believe me, this C actually stands for compact, even though you can see the comparison to the size of a human being in this picture. This is like 50 meters high, 20 meters long. And this is called compact because the other experiment is even much bigger than this one. And sometimes I learned from Beate, the director of particle physics here, that CMS may stand for Cabernet, Merlot, and Syrah. But anyway, this is an experiment you do to study particles created by the little bang. So the other experiment is called ATLAS. The people at DAISY are involved in both experiments. And they produced this public outreach video before they started the construction. So you see that particles come together, they get smashed in the middle and produce a bunch of other particles. You try to collect them all to understand what happened. Now you see what movie they had in mind when they produced it. And they're pretty serious people. They go all the way to do that. So these people come from all around the world, thousands of them working together. And after working many, many years, they managed to discover the Higgs boson. When protons get smashed with each other, that produces the Higgs boson, and it is integrated right away, into two photons, which you see in these green colors coming out of the disintegration of the Higgs boson, right up there and down there. So Higgs boson is there anyway. So what you have to do is bring these high energy particles together and put a lot of energy into empty space. It's like taking a big hammer and then whack the empty space. Because Higgs boson is already there, it just pops out. But after it popped out, it decayed right away into two photons and what they managed to observe. So we really know now that Higgs boson is everywhere in empty space. So that's what colliders do. This is actually an incredible machine. So what they're accelerating right now is a particle called proton, And that proton is not that heavy object among all particles we know of. So it is sort of like a little tricycle. Here's another tricycle. It's light, but you pedal it like crazy, bring it to incredible speed and energy, and smash them against each other. And the energy you put in by pedaling the tricycle now gets converted to mass, and out come an airplane and tanker. That's what colliders do. We have seen many new heavy objects coming out from collider experiments. And in particular, if one of them is the Higgs boson, which may actually talk to dark matter, which is actually quite likely from theoretical point of view, and if it does, the produced Higgs boson may disappear into the dark universe, and you don't see anything there. But you can still tell, because there's an airplane over here. If there's a heavy airplane over here, there must be something down here to balance it out, but you don't see anything, which means you managed to create something invisible. That's the way we want to study both the Higgs boson and Higgs boson possibly talking to dark matter. So this Large Hadron Collider has been doing a great job, discovered the Higgs boson already. It continues to run to increase the data size by a factor of 20 or so. So we are looking forward to see many, many more discoveries in the coming years. But we also think that it would hit the limit at some point. Whenever you smash these protons against protons, what you see is actually big mess. And if what you're looking for is one of them not seen because it's invisible out of this mess, and that's obviously not an easy thing to do. Now, the image is shaking means maybe there's another collider being built right here. I don't know what's going on. So let me unplug it and plug it in again and see if that fixes the problem. It did. Great. Sometimes theories can also do practical things. So the reason why it's such a mess is that smashing protons against protons is sort of like an experiment where, ooh, what is going on? Let me, that's right, change to a different port if that fixes the problem. At least for now, we'll see how that persists. No. What is going on really? Let me start it up again. It's doing the same thing. Okay. No, it's the same. So it's not an issue with the adapter.
Just go to the next slide, please.
Ah, okay, good. All right, so the reason why we see this kind of mess is that smashing protons against protons onto each other is like playing with Flammkuchen, which is my favorite German food. It's doing the same thing again, against the Flammkuchen. And obviously when you do that, then all the crumbs will fly apart. And that's the mess we are seeing, because the proton is a very complicated object made of quarks bound together with something called gluon. So that's why we think at some point, then it becomes very difficult to look for some new phenomena using this proton-proton experiments. Okay, at least it's okay, so we will see. So the idea is that even though you're smashing a Flammkuchen against Flammkuchen, what you're really looking for is that the C's in the olives would hit the C's in the other olive. That's the kind of experiment you're really looking forward to. And if this produces so much crumbs, and the naive idea is that, well, then why don't we just throw the olive C's against the olive C's from the very beginning? And that's the idea of an experiment based on electron and positron collision. Electron is a particle which has nothing inside, it's almost a point. So it's an antimatter a particle called positron. So you're really smashing something which is elementary against each other. So you don't have these crumbs to worry about. This is actually not very good. I'm sorry? Oh, okay. So you think the Flammkuchen is the problem with this? Okay. All right. So the idea is that by doing this experiment using olive seed instead of Flammkuchen, you may be able to see what you can't at the Large Hadron Collider. So the difference is something like this. You get a more crisp picture of what you're looking at. So if you look at this picture, you might think, oh, this must be a picture of Einstein. But if you actually make this picture with better resolution, you find that this is actually my son dressed as Einstein on the night of Halloween. So this way, if you actually smash electrons and positrons, you can pick up things very, very clearly. So this example shows somehow out of the collision, two particles came out. In this case, they are called muons. And if you look at from the side, it looks like this. Then immediately you notice, there's something strange. We seem to be missing something that must have gone that way for everything to balance out. And that's not easy to do if you're smashing protons and protons, because the crumbs of the Flammkuchen actually keeps moving along the direction of the beam. So you don't know how much you have lost in those directions. Then you don't know exactly what you have, what you're not seeing in this phenomenon. So by using the electron and positron, you can see phenomena much more clearly than you hope to be able to pick up these rare events where the Higgs boson might actually have disintegrated into the dark matter. There's yet another important question we'd like to ask. That's about the antimatter. So I already told you that positron is an antimatter of electron, and this is the first example where people made antimatter artificially using an experiment in laboratory. And from these experiments, we learn that whenever matter is created from energy, it's always created in 1-to-1 as a pair of matter and antimatter. And also when antimatter meets matter, we know that they actually disappear and annihilate back into pure energy. Again, that's always 1-to-1. And even though antimatter might sound like a science fiction, this is actually being used in hospitals these days for cancer therapy and cancer diagnosis. So the antimatter is something you can find even in hospitals. But of course, the word antimatter captured the imagination of many people. There is a movie based on a novel by Dan Brown called Angels and Demons. And antimatter is the theme in this movie. At the beginning of this movie, a scientist at CERN laboratory produced a 1/4 gram of antimatter without the knowledge of the Director General. And you see the Director General actually later in the panel, Fabiola Gianotti, so you can ask her about that. And this antimatter falls into wrong hands. It's a pretty exciting movie. So you see, the fire going on, a helicopter flying, and eventually come to this CERN experiment, and apparently, this is antimatter. And it has to be suspended in the air, because the minute antimatter touches the wall of this vessel, they start to annihilate and produces a huge amount of energy. You need to avoid that. So that's why antimatter is suspended in this tube. The problem is that this falls into the wrong hands, and this bad guy takes this tube down to some underground location in the Vatican. But this tube is actually operated by a battery, so it would eventually run out. You can't suspend antimatter in the air anymore, and there's gravity. Antimatter would fall on the ground. Unfortunately, the floor of Vatican is made of matter, so matter and antimatter meet. And you shouldn't underestimate this. Even a 1/4 gram of antimatter actually produced an explosion as big as atomic bomb in Hiroshima. So you don't want to see that. And unfortunately, it didn't come to that in the movie. But the thing I was most impressed by in this movie is the following fact. To produce a 1/4 gram of antimatter, just the energy bill is going to be billion, trillion dollars. This scientist spent so much money, and Director General didn't notice it. CERN should have an incredible budget. But anyway, so we can confirm that Fabiola later too, but we really don't avoid this. So we can't produce that much antimatter for obvious reasons, because we don't have enough energy. But Big Bang did. So when Big Bang produced matter from energy of the Big Bang, then it produced antimatter at the same time, 1-to-1. And if it stayed that way, eventually the produced matter and antimatter would meet as the universe expands and gets colder, and then annihilate with each other back to pure energy, and that's the complete annihilation. So what we know is that somebody saved us from this complete annihilation. What must have happened is that after the matter and antimatter created 1-to-1, somebody changed 1 out of billion antimatter into matter, and this might have been also the role played by the Higgs boson superhero. And now there's a difference of 2 out of a billion. Eventually, matter and antimatter meet, and what remains is us. So we all survived at the expense of a billion friends. First of all, we should be thankful to them. But second, we really need to understand how somebody managed to shuffle a little bit of antimatter into matter so that we could survive. And so we need yet another superhero here. And there is a theory that says that this superhero is again the Higgs boson, who saved us from complete annihilation. That's why we would like to build a new collider experiment to smash electrons against positrons in an environment that's very clean, without crumbs from the Flammkuchen. And one possible design is a linear machine like this. And you see this yellow tube throughout this machine called the cryomodules. And in these yellow tubes, you start to accelerate the electrons and positrons in the opposite direction by using powerful radio waves. So it's like a surfing. When you have a wave that would push the surfer and make it faster and faster on the way, and after it gets sped up, they get smashed against each other. And because it's not Flammkuchen, there are no crumbs flying apart, and you get to see the very details what's going on. It turns out that even though this technology was developed for the purpose of particle physics experiments to understand the Big Bang, this is actually now being used at this laboratory at DAISY in an experiment called X-ray free electron laser. So this technology is now being used for photon science, which spans from health and biology, energy, catalytic processes in chemistry, information technology, and technology transfer to the industry. So this is actually being extremely useful, not just for understanding the Big Bang, but also studying many other things, including medicine. Beyond this, we don't have a clear idea yet, because we don't know what kind of machines we can build. What we know now is this idea of smashing electron positron at high energy to produce many, many Higgs bosons is something we believe we can do. There's one design based on this circular machine, another one based on this linear machine, and using these machines, we start addressing these questions. Why do we exist? Why did the Higgs boson freeze in the universe? Does Higgs talk to dark matter? Who saved us from complete annihilation? And this is actually very also connected to many other fields of science. I told you already that we learned from superconductivity to come up with the idea of the Higgs boson. We may even use superconductivity to build some of these machines as well. And some of them have gone back to medicine for medical resonance imaging, or also cancer therapy, that you actually send a beam of particles using accelerators to kill the cancer cells to cure your disease. I already mentioned this XFEO at this laboratory, which is used in many, many different disciplines. We can also study the structure of the protein, which is important for biology and also medicine. We all know that CERN invented the World Wide Web, which is the basis of trillion-dollar industry in electronic commerce these days. And some of the concepts we learned from condensed matter people, we are also providing some concepts to them as well. One concept that went from particle physics to other disciplines is something called the Majorana fermion, which is believed to be actually very important for the future stable quantum computing. And as we already talked about, we have a lot to share with the astronomers to understand what the universe is made of and why we exist. So the particle physics experiments using these colliders is relevant to many different fields of research. And what would happen beyond then, of course, depends on what we're going to find about the Higgs boson. We need to meet the superhero first, ask him what we should do next. There's an idea called a Future Circular Collider to build a bigger machine than the current Large Hadron Collider and smash protons on protons again, and that would require new technology development of very strong, powerful magnets using these superconductors I mentioned just a minute ago. There's also another idea, especially in the United States, to use a big brother of the electron called muon, which is 200 times heavier than an electron. As a result, you may be able to make these machines smaller 200 times, and then it's smaller, and we're hoping it could be cheaper as well. And at this laboratory, DAISY, there's also new the technology being developed based on what is called a laser plasma acceleration, and potentially this technology can bring the size of these collider experiments 1,000 times smaller. And that's the way we hope to proceed with the affordable experiments in the future. So I've been talking about this question, why do we exist? I told you that these big questions need collaboration of all sciences, particle physics, material science, biology, astronomy, chemistry, even medicine, or possibly even philosophy. And I want to make the point that this kind of science has to be done in a very inclusive fashion, involving many disciplines, people from all around the world. I happen to be invited to give a speech about this at the United Nations headquarters in New York, and referring to the institute I founded in Japan, Institute for the Physics and Mathematics of the Universe, this is how I concluded my speech. To make it clear that institute I founded in Japan is open. Let me do it again. To make it clear that institute I founded in Japan is open to anybody, irrespective of their origins, I named it the Institute for the Physics and Mathematics of the Universe. Laws of physics and mathematics that describe these laws are not applicable to the entire planet Earth, but also throughout the whole universe. One day, I hope to see a job application from a different planet. I would think it's only a matter of time. Thank you so much for your attention. See, I'm an optimist. So anyway, we talked about a superhero. We really need to meet him, understand him better, and so that we know why do we exist. And that's the reason I picked this title, Higgs boson, particle superhero, Hector Super, and tour guide to new particles. Vielen Dank.
Thank you so much. Thank you very much. So we have a panel discussion coming up, but we're very happy to take, Toshi is very happy to take any direct questions now from the audience in the room, at least, on aspects of the talk. So now's your chance.
So Flammkuchen is really a problem, I learned.
Yeah, don't ask why the video flickers on Flammkuchen, please. Yes, we have a question here. Can you?
Francois?
Thank you so much, Hitoshi. We have been knowing each other for a long time. And so I want to ask a very intimate question.
Oh.
How do you explain this fine-tuning, this providential fact that we exist? How is it that it works? I mean, is it accident? Is it something which was built in the laws of physics? Is it something magic? This is the most mysterious aspect, I think, of the universe.
You know, I completely agree with you, and that's why I mentioned that this range of the weak force needs to be made just right so that we can exist, which is very, very mysterious. And I hope that there is a good explanation to this. It's not an accident. There is a reason why the range of weak force comes out the way it does to make sure that everybody in the universe sort of work together. And so there are several ideas. One of them is called supersymmetry. Another one is called extra dimension. In all of these cases, at least you need to have extended laws of physics, which we don't know at this moment yet. And we hope to see the first hint of those new laws of physics by studying the Higgs boson. So Higgs boson is really meant to be a tour guide. It opens up a new window so that we sort of peer through Higgs boson into the new world, which we haven't met yet. So at least that's the hope.
So we have to wait.
Yes.
I think yes. Yeah. Are there any more direct questions now on the talk? Alan? We have one here.
So you introduced the Higgs boson as a superhero who will solve all these problems, but it may not be the Higgs boson who solves all these problems. Are there other possibilities?
Well, at least we know Higgs boson is the superhero who keeps us together. So that part is clear, and that's why we would like to understand it better. The other role of superhero I mentioned, namely being able to talk to dark matter, they may be really saved us from the complete annihilation. They may have been played by some other mechanisms than the Higgs boson. So we just don't know. So the great thing about these new colliders we talk about is that it is at least guaranteed we get to know the superhero much better than we do today. So that is guaranteed. But in addition, we hope we start seeing some of these different roles Higgs boson played by doing this experiment. So that's the excitement, at least to my mind.
We have one, I think, a final question before we move to the panel.
Well, when you introduced your Institute of Mathematics and Physics in United Nations, which type of tuning did you observe after this presentation in the United Nations?
Which type?
What was tuning reaction?
Oh, the reaction was actually very positive. And it was really heartwarming to hear from the delegates to the United Nations from many different countries that they really want to put science at the policy table in their wording. So science was missing in much of the policy decisions in many countries. Germany is kind of special because it was led by physicists for many years, but most countries don't have any scientists involved in policy making. And so the UN really cares about, climate change and all these issues, which have to involve scientists to solve them. And I know that Fabiola, who'll show up on the panel soon, was actually on the advisory panel to Bang Subom Kim, some of the earlier Secretary Generals of the UN. So they really seem to care about science. So that was the most sort of a great thing I learned by going to the United Nations.
Thank you. Okay, one more.
Is the mass of the proton or neutrons due to the Higgs boson?
Say it again?
Is the mass of the protons or neutrons, are they due also to the Higgs boson?
No, it's not. Mostly it's actually due to the motion of quarks inside a proton. So when you actually put these quarks inside the cage of protons and neutrons, they actually move pretty fast inside, and they have kinetic energy because they're moving, and that's mostly the mass of a body. So if you put yourself on a scale, you are measuring how quickly quarks are moving inside your body.
Okay, thank you very much. Actually, can you pass it behind you? Oh, thank you very much, Hitoshi.
Right.
Thank you, Hitoshi, again for that. And he's going to stay with us to join a panel, but he gets some help this time from some experimental physicists as well. We'll move over to these chairs now, and I think we'll get two of our panel members on the screen. If the other panel members could come forward as well and find their seats. This one's mine. So yeah, I think so, yeah. Very good, thank you. So this should be, we hope this will be a fairly informal discussion that will follow on from the theme that you've just heard outlined, the big themes that you just heard outlined there. So apart from Hitoshi Murayama, who you've already been introduced to, maybe I should also say who I am. I don't think I did that first time, but I'm an experimental particle physicist. My name is John Butterworth from the University College London. And then we're joined by Carl Jacobs, who's chair of the European Committee for Future Accelerators, which is one of the organizing bodies of this whole meeting, and is also an experimental physicist from Freiburg. Then we have Beate Heinemann, who's also an experimental physicist and is a research director for high energy physics here at DESY. That's why you saw her with the wine bottle and Hitoshi earlier. And then we have Ferencia Knelli, who's an experimental physicist from the University of Zurich. So welcome everybody, and thanks for joining us here. And then on the screen, we have Jesse Taylor, who's a theoretical particle physicist from MIT, who's currently in MIT, I believe. And Fabiola Gianotti, who's the Director General of CERN, who you've already heard her name taken in vain several times already, who's actually not in CERN, but in Granada, I believe. But thank you all for joining us. So welcome.
Ciao, hello everyone.
So what we kind of, it's a vague plan of this, and we will be steered by the audience, and not just the audience in the room, but also the audience online who are submitting questions. So when I'm looking at my laptop, I'm not doing my email, I'm trying to find out whether we've got any good questions coming in from our moderating team over there. And we thought we'd try and group them into three broad areas, one of which is directly following on from that talk, really, which is the science drivers of this kind of project. Then we thought we'd spend a bit of time discussing the technology and how you actually enable such a large project, we hope. And then finally, we'll talk a bit more about the societal impact of the project and broaden the discussion out. That's just a very vague outline. We will be guided by what kind of questions we get in, and we'll see, and what kind of answers we get from the panel. So I think, though, to start, since we've had a theorist talking for 40 minutes about their motivations, maybe start with one of the experimentalists, Florencia. Maybe you could, looking at that outline of the physics and the motivations that Hitoshi's given us, maybe you could say, what is it as an experimentalist that drives you? Or is it one of the motivations he's given, or is it something else?
Is this on? Yeah, okay. Okay, thanks and good evening. First, it's going to be very hard to follow that exquisite and eloquent talk by Hitoshi. So I'll try to add a bit on maybe from the experimental side, as you mentioned. So this is very loud. Sorry.
Maybe it's me.
Is it really loud?
No, it's okay. It's good. I think
Okay.
there was a slight
Because
echo,
it's
which
here.
might be coming from there. Yeah.
Okay. Okay, sorry. So I'm an experimentalist, and I just wanted to say I've been in 4 hadron collider, in 4 experiments, and in colliders and 2 hadron collider physics. I've never done physics myself on lepton colliders, but before going into that, I just wanted to mention mainly the recent progress and what to expect that is coming now from the current experiments that we have running on at the LHC. So as you know, the LHC was designed with the goal of finding the Higgs and also explore a large amount of territory of new physics or physics or new particles and interactions. It has done a superb job in the last 10 years of running by not only finding the Higgs, but also finding the interactions with the standard model particles, with most of the standard model particles. It has also explored a vast territory in comparison with what we had before the LHC to now on scenarios of physics beyond the standard model of the physics that we know. In the future, we continue to run for more than a decade, and we'll have much more statistics. It will collect much more data, and will have much more precise results on many aspects. That being said, there is a limitation on that. So even though it will continue to explore and will give us many answers to Higgs and other standard model particles, and also explore more territory on new physics, there is this limitation, the Hitoshi is the Flammkuchen limitation, that
makes the whole experiment flicker, right?
Exactly. And that even though with more statistics, we cannot see, our measurements are a bit fuzzy on what we can see. And for that, if we want to get deeper or to get deeper knowledge of the Higgs boson or other particles, we need more clarity, and this is what the leptons offer. from the experimental side, as far as collecting more data and having all these statistics, and also we have done a superb job also with the detectors and upgrading the detectors, and also on have many analysis, innovative analysis techniques that have improved and pushed the boundaries as much as we can. There is this limitation underneath. That is the fact that we collide protons which interact with the strong force, and then there's large amount of backgrounds that we have, and other caveats and little things that make all our results a bit more faster than what we would like to try to see effects of interactions that might be more feeble than what we currently can see. So because of that, that is the main motivation. But that also I wanted to add, not only for the Higgs, this is important. The Higgs can maybe perceive or feel some feeble interactions with the dark matter. The dark matter, as we know, is can at most interact weakly with the weak nuclear force. And so we know that there has to be more feeble or more interactions below. So this is one of the probably most and touched by Hitoshi, most important maybe, for me, in my opinion, of things to explore. But then there's also other things, right? For instance, right now, there's also more studies on the W boson. Currently, there is a measurement that is in disagreement with the standard model. Getting to that precision will be quite important. Then there's the top quark, for instance, which has only been produced and studied in Hadron Collider. So with Hadron Collider precision, studying it with precision in a lepton collider will be quite crucial. It is at the end still a very special. It has still the crown of a very special quark, being 40 times larger than the next, the big quark. So I think that why going in this direction is, again, is the clarity and the precision that we have. It will be very complementary with the knowledge that we have already acquired. And just one more thing, that to say that even the Higgs boson did not just fall in our lab, right? So it's not that we put the LHC and then found the Higgs boson. There was a preparation towards that, not only from the theory community, but then there were many measurements done mainly at lepton colliders that have guided us to be able to corner the Higgs where we want it. So it was not something that was just on the LHC being built and found. So it was something that we gathered enough information, and that information that came from the lepton colliders that ran before were crucial for it.
Okay.
Okay.
Thank you. Are there either of the other experimentalists in the room want to add anything quickly to that? Was that covered quite a lot of ground there, I think, right? Thank you. Okay. Another question that we have, which maybe I'll throw to Jesse as one of our people on video there, is, and this is, I guess, because we're sitting in a lab here, and obviously national laboratories and laboratories like CERN have a huge job to do in providing these facilities, but most of us also work in universities. And one of the questions is, how does it feel, and what's the impact of these large projects on early career scientists and students, and how does that work, joining such a big... What's the attitude from students and early career scientists, Jesse? Maybe you could speak to that a little bit from your experience?
Sure. Well, it's a thrill to be called an early career scientist, and it's also a thrill to share the
I was talking about your students, Jesse, not you.
I've known some of the people on the stage here and on Zoom, for the entirety of my professional career. So just to give a little bit of context, I got my PhD in 2006. And after a little bit of an incident, the LHC turned on for real in 2010. And some of the work that I was doing that's most influential came from my work around 2010. And certainly when I was growing up through the system, there was a sense of build a machine, build a collider, and the ideals will come there. But it's important to know what that collider development will be, and getting a sense of which way the field is going to know where, as a theorist, I need to put my intellectual energy to. And so even though I'm a theoretical physicist, even though I was trained in particular in the same institution that Hitoshi comes from at UC Berkeley for my postdoc, my work is informed by the experiments that are on the horizon, the things that can be done in my lifetime. And for the current PhD students, when they're looking out at the field, what they're seeing is that there's an enormous discovery opportunity already on the table with the high luminosity running of the Large Hadron Collider. So the Large Hadron Collider will have another life with roughly 10 times more data, the same energy, but far more information. And that more information is pushing folks of my students' generation towards thinking about what you can do with precision calculations, what precision studies of the Higgs boson you can do, what are rare things that you can search for through this mass amount of data that's coming up. And in those investigations have then inspired them to even not only a Higgs factory, the opportunity to do those explorations in more detail, but even beyond that, the level of precision and the level of exploration that you would need to do to answer some of the questions that Hitoshi mentioned. And so I would say that among the younger generation, there's enormous amount of excitement about the things that might be on the horizon, but there is this challenge that this is a multi-generational effort that we're involved in. If you think about the standard model of particle physics, we've had this for a half century, and one of those ingredients was only discovered in 2012. And yet we still have questions that were similar to the question that I had as a PhD student. And so I think there's a clarity about the direction that the field needs to go and the types of theory as well as experimentation that needs to be done to get us there. But there is conversations, which we can have more conversation about the timescales involved in these big endeavors, and making sure that we're investing our efforts both on the theory side and the experimental side to really tackle the key questions that are facing our field.
Thank you very much, Jesse. Is there anyone else like to add anything to that question or that comment? Okay, so we have a question that I'll get your questions ready in the room because I'll ask the room in a moment, but we have a question online, which is referring back to the problems in Hitoshi's talk, is that why haven't these open questions already been solved by the Collider projects of the past, including the LHC? The question says, I remember hearing some of these questions being asked 20 years ago and they're still not answered. So why is that? What's the case?
Well, at least for the Higgs boson, we basically just met him. It was discovered 10 years ago. That's a very brief period in the history of science. So there's still a lot we haven't understood about this new superhero. So we need to study more of it, and we need to talk to him, and we get more information. So that's definitely something we have not been able to do in the past. On the other questions like dark matter and antimatter, if we were lucky, we might have seen some glimpse of answers in the past experiments, but nature wasn't so generous to us. So they are still waiting to be discovered and understood. So we have to keep trying. And in each case, there's no guarantee that the next generation of colliders actually answers those questions. But at least I see a good chance of that happening because that's a territory we haven't explored before. So that's an opportunity.
Okay, thanks. Beata?
Maybe one way to illustrate it is with the Higgs. The Higgs could decay to dark matter. And when it was discovered, basically it was possible that nearly all of them, the way the Higgs boson was observed was in a very, very rare decay. So there was in principle, there was a huge opportunity that 90% of the Higgs bosons could have decayed to dark matter and we wouldn't have known at that moment. By now, we basically know that it's at most, I think like 10%, if I'm not mistaken, 10 to 12% are the current limit right now. So we already know but it might still be 5%, might be 2%. And with more and more data, we'll just know better, right? With high luminosity LHC 2%, and with the lepton machine here, we're probing it at the Fermi level.
Yeah, right.
So this is so it's just really the power of both statistics and having the right machine together that you need to check some hypotheses like this, like does the Higgs actually decay to dark matter or not?
Agreed.
Thanks. So are there any questions in the room that people would like to either follow up on those or completely new tacks? I do have a stack of questions here already, so you don't feel under pressure. But yes, thank you.
Okay. My name is Rupert Leitner. I'm from the Charles University in Prague. It was an excellent talk, Hitoshi. Thank you very much for that. And I have a question, because today we know very precisely the property, or quite precisely the properties of the Higgs boson. In particular, we know that the rate of the production of the Higgs boson is in accordance with gluon-gluon fusion of proton. This fact is almost excluding the existence of the fourth family of quarks. Am I correct? And do you think it's true? Is the discovery of the same importance as the discovery of 3 families of neutrinos at lab? Thank you.
That's right. So thanks to the discovery of the Higgs boson, we can now put a much better information on this question, whether the nature would repeat 4 times instead of 3 times. The answer turned out to be the clear no. So we're already learning a lot of stuff, having discovered one new particle that comes with all the extra information, and that's the way we hope to learn, and we will learn more, and that's exactly the way the field will proceed.
Okay, thank you. I have a question. Go on, Carl.
If I can just add something. I mean, as you pointed out, the major production process in the discovery was the gluon fusion, and then you go via a virtual contribution of heavy quarks, the top quark, and already very early on at the LHC experiments, we were able to rule out contributions of a heavier fourth generation.
Okay. An impatient question from online, which is, maybe this is best directed to Fabiola as the Director General of the Big Lab, which is, why does it take 20 years to get a better look at the Higgs? Can't we do it quicker? And if not, why not?
Well, it takes a lot of time because, well, first of all, we have today still an instrument, the LHC, and then through its upgrade, the high luminosity LHC, which will continue to study the Higgs boson. Was mentioned that the amount of data that we will collect at the end of the lifetime of the LHC and the high luminosity LHC will be 25 larger than what we have today. So that's really will allow us to make a big step forward in the study of the Higgs boson and many other phenomena. Now, it takes time to build the next collider because, of course, it needs new technologies. It needs resources, human resources, it needs money, and building these machines, even a very compact collider, requires civil engineering work, requires excavation, requires a lot of work that you cannot do just in a few years. So I think it's very important that while we are still operating the Large Hadron Collider, we already start to plan and to build the next machine. So as to continue our exploration without break, and also it's also something that brings us back to what Jesse was discussing before. It's very important for the young people to be able to to work on different things. When a collider is running, like the LHC, then of course people are working mainly on data analysis. When a collider is under construction, the young people can also work on hardware, on the detector development, R&D. And so having the possibility for a young person to work at the same time on analysis, data analysis in a machine that is running, and at the same time working on detector R&D and planning and working for the next collider, that gives you a much broader, spectrum of opportunities. So I think it's very important that we start now thinking seriously to build the next machine.
Thank you. Anyone want to add anything? I think that was pretty clear. It's not going to happen super quickly because there's a lot involved. I have another question here, unless there's another question in the room that someone would like to come in with. Okay, we have another question from online, which is, and you mentioned Hitoshi actually very briefly because you had not much time and a lot in that talk, but you meant in one of the answers, why is the Higgs so light? You mentioned a couple of candidate theories as to what keeps the range of the weak interaction essentially where it has to be to allow us, and that was extra dimensions and supersymmetry, which are examples of theories that predict new particles, right? So why do people keep predicting and looking for new particles that are really unlikely to exist? What's going on there?
So the looking for new particles may be a little misleading way of putting it, because we're looking for new symmetries of nature, new laws of physics. They happen to come with extra particles. So it's not that we are just simply hunting for new particles for enjoyment. We're really trying to understand deep level what the laws of physics are, how universe work, what symmetry controls them. And if those symmetries happen to come with new particles, that is a way of discovering a new symmetry. So the particle, in some sense, is a tool for us to understand all the mysteries of the universe at a really deep level. And that's the way I view it.
Umberto and Carl.
Actually, I hate the word particle physics for that reason, because in some sense it's misleading. I really like much better how it's like, you know, the Institute of the Physics and Mathematics of the Universe, because I mean, what particle physics is trying to understand is really the initial universe, right? How the universe came to be, and which is why we're here, which Hitoshi put so brilliantly. And somehow the term particle physics is just not capturing that. It sounds like zoology rather than, nothing against zoology, of course, but...
Or stamp collector or something.
Carl, you have a microphone now.
Just to add a bit on this, I think as well, you know, we are driven by these symmetries, and these symmetries come with new particles. And of course, it's also quite natural to look for new particles in the context of the big problem you discussed on the dark matter. Yeah, and there are theories which predict dark matter particles, certain nature of them. And I think it's our obligation to look for these particles in these powerful accelerators. And especially, I think the problem of dark matter, you need to also to illustrate and to explore from different angles. So we have direct experiments which look for direct scattering of dark matter particles. I think it needs to be complemented as well by a different process, which is the production of these particles in a collider.
Mm-hmm. This is another question online, actually, and it follows on, I think, from that quite well. Excuse me. Which is, you were talking, and we're talking here with an E plus C minus machine about doing the benefits of precision. This is where Florencia came in at the beginning as well, from an experimental point of view, and from the point of view of studying the superhero more carefully. We're focusing on precision, so we're looking at differences in physics that show up at the level of 1% or less sometimes. Is that natural? Why would they be hidden like that? Is that a natural situation? Most things we see in nature are not hidden like that.
Can I answer that question?
Yeah, go ahead, Jesse.
Well, it's fun for me to answer that question because I was just explaining it on the blackboard over here, and maybe you can't really tell. Yeah, so you know, I'm a professor at MIT, and I have students who come into my office who ask, you know, why is it that I should focus on doing calculations to the 1% accuracy level? And what was said before is totally right about the fact that it's not just particle physics. Those particles are related to big ideas, and then you can take those ideas in the context of quantum field theory, and you can estimate how much precision you need in order to answer some of the questions that Hitoshi was talking about. And this back of the envelope thing that's on this board here was explaining why, if you don't do better than 10% accuracy, then you really can't address these deep fundamental questions. And so accuracy ends up being the inroad in terms of answering these big ideas. And it's something that falls out of the structure of quantum field theory. I would love for it to be different. I would love for big ideas to have big manifestations, but oftentimes you only see them in these subtle deviations that require both heroic experimentation and heroic theoretical calculations.
Thank you. Anyone want to add anything else to that? No? So, I guess we've sort of done quite a lot on the science drivers of this machine now, and we've also actually already, with the questions Fabiola touched on, what it takes to actually build one of these machines. One of the questions we've had in here is how do the PhD students that Jesse was talking about, the young scientists already involved in the field or coming into the field, how do they influence the choices? How do the decisions made? How do people have a say in this? Perhaps as ECFA chair, Carl, this is in your ball first, but everyone else can.
I can try, and then others can add in. So I think in Europe and also very recently in the US, the field went through a process which is called strategy building, and I think this is open to the full communities. So this is really a bottom-up approach. In Europe, we did this over the years 2019 and 2020. And in the US, it converged very recently. So it's open to the full community. And also the early scientists have a voice there. For example, in the ECFA, we have introduced an early researcher panel, and they also can bring their view into this general discussion. Mm-hmm. Of course, the decision-making has to be taken up at a higher level.
Okay. Any other comments on that? I mean, that actually does lead on to another question, which is, of course, particle physicists do not have the power to decide to spend this much money on a machine, whatever machine we say we like. How do we make the case to do that? So we're getting maybe in towards the societal impact issue of this, but how do we persuade society, and why should society spend such a lot of resources on answering questions like, why do we exist, for instance?
Can I try?
Yeah, sure.
John?
Yeah, please go ahead, Fabiola.
Yeah, so first, I think there are two aspects to this. First of all, I think how much money is society ready to put on the table to understand fundamental question about our existence and about the universe? Is there a limit to knowledge? And so this is the first question, is the intrinsic value of knowing, of exploring, understanding, investigating, and understanding how things work. This is something that is intrinsically related to our nature of human being as clever beings, and that we have been exploring since the time the first human being appeared on Earth. This is the first thing. The second thing is that fundamental research is, we know from history, not just in our field, is a driver of innovation, because fundamental research nowadays in many fields requires cutting-edge technologies that do not exist at the time where we need them. And so it drives the development of industry, it drives the development of technologies. Some technologies will never be developed or will not be developed so quickly and so well without the driving force of fundamental research. And these technologies, of course, are made available to everybody free of charge. And Hitoshi alluded to the impact of particle physics on medicine, on many other fields that go from, big data to electronics, cryogenic, vacuum. And so I think that these are two important elements. Another important element is that the field also is educating and training and raising thousands and thousands of young people who do not stay in particle physics because the number of jobs in the research is limited, but they go out to society, they go to industry. And so there is a lot of added value to what we do that goes beyond also the very valuable goal and already justified by itself to understand, to answer the fundamental questions.
Good, thank you. Yes, Carl?
Yeah, I would like to add, I completely agree, of course, with what Fabiola was saying. I think, these are big questions, and it's in the nature of human beings to be curious and to answer such great questions. This brought me, for example, to particle physics. When I was at CERN for the first time, I got so motivated, say, this is the place where you want to work. So big questions, and I think it's important that we try to answer these questions. They add to the cultural heritage as well of mankind. And I think as well, it's very clear that fundamental science is a driver for technology and innovation. We have seen this in many, many places, and I'm sure it will continue to be so. And also it is important, what Fabiola said, we see this, most of the PhD students, of the young students which we train up, they get trained in, I would say, a fierce competition at CERN in international environment. And they learn many, many skills in our field, which are also useful for their future career outside of science. So I think we give also a lot back to society. And if people from time to time say the big accelerators are very expensive, one has also to compare this. Take the LHC, the big machine. It's in operation since 2010. It will run for another 20 years from now. So this is in total 30 years. It's a research infrastructure which is used over a very long time span, 30 years, by many scientists. We have 23 member states at CERN. CERN is open for worldwide collaboration, and they all use this facility. And if you break this down to a typical university group, I think the budget is not is comparable, probably.
Hitoshi?
I know many countries have a lot of emphasis on innovation these days, and always an example that comes up is like iPhone. But when I was listening to some keynote speech by Steve Jobs himself, he claimed Apple is not a technology company. That's a company at the intersection of technology and liberal arts. Without liberal arts, knowing how humans function, what is the best way for us to deal with the phones, they couldn't have built iPhone. And particle physics, in some sense, is a big liberal arts with technology. We are really pursuing big questions by humanity. And I think humans became human because of their curiosity that really distinguishes us from other animals. And that's why we invented so many things. We started to use fire ourselves and came to our stage of a highly evolved, intelligent life form. So if we start actually losing doing this kind of curiosity-based research, we are no longer human in my mind. That's the way we make progress. And I really hope that we keep doing that.
Thank you. Quite big stakes. We have another challenge to the same along the same lines, so that I think it would be useful to address and see. I mean, the world's changing very quickly, and we know that the climate is changing, and we're seeing the effects of extreme weather, and a lot of that is human generated. Is it justifiable to be using this much energy to answer questions like where did we come from in that environment?
Well, of course, it's difficult now. The issues with the energy and people dying, everything's horrible. The one thing which was really amazing about CERN is that it was founded in aftermath of World War II, when entire Europe was devastated, and it was created for the purpose of reuniting Europe by using science as a common purpose, and it worked brilliantly. So right now, we can't do that, unfortunately. But the minute the war is over, we start rebuilding the trust among different countries and people. And science would be enormous help to achieve that, at least in my mind. Fabiola should, of course, chime in as the DG of CERN. But I'm a true believer of this idea.
Yeah, maybe.
Fabiola?
Yes, thanks. So first of all, I think the problems of climate change, environment, sustainability, etc., cannot be tackled without the input and the contribution of science. So science really must be center stage to address these challenges. So for point number one. Point number two, these challenges are global. They are global, and so they require really the collaboration and the work and people working together across national borders, across discipline, across sectors, etc. And so, and particle physics gives a good example on how to collaborate and work together. And again, tackling these challenges requires really new technologies, and fundamental research can help in that respect. Some of the technologies that we develop at CERN, like superconducting links and things like that, could be used in the future to transport electrical current without losses. So with the gain in terms of electricity and energy consumption. Clearly, our facilities, we have to work to minimize the impact on our facilities on the environments, something that we have been doing at CERN now for many, many, many years. Every 2 years, we publish a public environmental report to show the progress, to show where we stand, to set ambitious but realistic goals. And we are working on sustainability, so developing new technologies to save electricity and energy. And these technologies, in turn, can be used also by society.
Thanks.
Maybe can I add, because I think I was another example, which I was reminded of when Fabiola said, is also that accelerators can be part of the solution. So for instance, actually here at DESY, we used to have the world's highest energy E+E- accelerator in the 70s called Petra. And this accelerator is still running today, now in its third incarnation, but it is now running for the purpose of photon science, exactly like the European Exfil. And also both at the European Exfil and at the Petra, there is, for instance, a lot of studies related to catalysis, which uses a lot of energy, or also to batteries, new batteries. So it's, if you hadn't ever had an accelerator, you couldn't have done that, and you can make progress there. And there's even another generation now planned. For instance, one can use permanent magnets, which is the plan where so I think minimizing minimizing the energy consumption is, of course, a responsibility we have. We should try whatever we can, or using also the heat, for instance, from cooling these accelerators, you get warm water that you can then use to heat the buildings and so on. So a lot of effort is done here, is done at CERN, to at least try to mitigate and use the energy as wisely and as effectively as possible and mitigate it. And I think that is important, but one also should spend as much as needed.
Mm-hmm. I mean, I guess you gave, you could say that was it called the Globotron, the collider that Fermi proposed? I mean, there's a cycle of doing more with less, in the sense that the LHC is a lot more eco-friendly than that would have been, for instance.
Yes, but then John, sorry, why we didn't need to build Fermi's giant collider? Because we invented colliders. So sorry, the Fermi was not a collider; it was a fixed target accelerator. So we invented. Yes, that's why it was so big, because to get a large energy in the center of mass, you needed a monster accelerator. So we invented colliding beams, and we have developed superconducting magnets. Yeah. So ideas and technologies.
We get smarter as well as bigger, I guess. Okay, good. Are there any questions from the room? We haven't had one for a while from anyone in the room. Does anyone have anything they want to throw in? Okay, maybe not. Oh, okay. Can we just get a microphone to you? No.
We have a good example of the fact that things which are completely speculative can find an application very quickly. The Nobel Prize was given a couple of days ago to people who were studying entanglement, for Christ's sake, which at the time was completely speculative, and now is raised as a pioneer to quantum computing. So this is really a great example of something that was totally very, very crazy, and that's gone something extraordinarily practical in front of it. So we shouldn't be worried about doing profound science. I think that it is recognized at the highest level.
Okay, thanks for the comment. Someone's clearly gone for the kind of the big vision of your talk here. Can we ever settle on another planet without discoveries in particle physics?
Oh, I don't know. Well, at least, it's not just particle physics, right? Astronomy, of course, people really love it because you see this beautiful picture of the universe, and spend $10 billion to build the James Webb Space Telescope, and because people believe that's worth it. So the kind of ideas that come out of these other basic research, not just particle physics, but astronomy and condensed matter physics, even biology, has a lot of relevance to people's interest in minds. And that's again, that's what I believe how humans are, and that's why this kind of research is something we should pursue. So that I'm just repeating myself, but that's my feeling.
Yeah, I'm not sure I'd know. I'm not aware of an application of the Higgs boson to a moon colony or something. There are actually proposals around to build particle physics experiments on the moon, for instance, where it's very quiet. Or maybe even a Fermi collider around the moon.
Lunatron.
But I think that's the other way around, right? Yeah. Okay. Good. Back to this business of new particles, though. We've had, and just to elaborate on it a little bit more, we've had every time there's a new collider, the theorists will tell us we're going to find all these new particles. The only one they've really been right about has been the Higgs, right, which is part of the standard model. So are we flogging a dead horse here? Are we refusing to learn from our mistakes?
John, sorry, can I say something here? So, I mean, of course, when you discover a new particle, of course, this is a big satisfaction. It's a glamorous thing. You get the headlines of the newspaper, etc. But take a machine like a collider, like LEP, and Hitoshi mentioned it in his talk. LEP did not discover any new particle. And is hardly a machine, an accelerator, a collider that has really had such a profound impact on our understanding of fundamental physics. It has put the standard model on solid experimental grounds. It has, made experimental evidence of gauge theories, etc. So, it's not just running behind new particle, it's running behind knowledge. What we want to do is to improve our knowledge, is to make step forward. If this means discovering new particles, fine. If this means, understanding how nature works at the most fundamental level, that's the goal.
I guess we're back to Beata's point that the field is poorly named. Particle physics isn't a good thing. We should think of a new name. Does anyone else want to add on that? Add anything on that?
I can add something. When I describe to people what I do, sometimes I tell people that I engage in rigorous speculation. So rigorous in that it's based on fundamental principles that we think might be true, not just in our universe, but perhaps every universe, but speculation about what the answers might be to some of the questions that Hitoshi raised. And part of that rigorous speculation is involving, predicting of potential new phenomena and new particles. And as we've gained additional information from cosmology experiments, from particle physics experiments, astrophysics experiments, we've actually changed the types of things that we think are more or less reasonable and diverted our attention to areas where we think that there might be different types of discovery potential. And so it's not just, oh, we're going to build a new collider and we're going to see new particles. Actually, maybe we can go back to old collider data and use new theoretical ideas to actually search for things that we might have overlooked. And there's a back and forth, a push and pull, where experiment gives us new information. And I think LHC has been spectacular in this case of verifying the properties of the Higgs boson to now look in different places and look for different cracks in the standard model in different places in different types of experiments that might reveal something in the future.
Thanks. Florencia?
Just one thing that I want to add, that there is information when we look for something and don't find it. We do get knowledge in some ways when we don't find something in places where we expect it, or in certain prediction from models or things like that. There is something also to be gained there as well.
Okay, thanks. I think we're approaching the end of the session, I think, unless there are more questions here. There was one question which actually was explicitly addressed to Fabiola, in fact, which was, if the standard model is on solid ground, why is everyone excited about deviations from it? Now, that was actually addressed directly at Fabiola, but I think all of you could have a go at that. I think it's a good question.
It's a good question.
You start, Fabiola.
Yeah, okay. So simply because the standard model cannot explain everything we see and everything we have understood. So Hitoshi was mentioning dark matter. We don't understand dark matter. There is no single particle in the standard model that has all the good properties for dark matter. We don't understand dark energy. We don't understand the matter-antimatter asymmetry. So the standard model works very well. Its predictions are very well demonstrated. All the particles predicted by the standard model have been discovered, but it's not a complete theory. There are many pieces that are missing. And so we are trying to make the next step and look for the theory, a more general theory, of which the standard model is just a part, that can explain everything possibly.
Yep, thank you. Carl?
Yeah,
Carl, then Beata.
Yeah, I just like to add to this, it is shocking for a scientist who does fundamental research that he's confronted with the fact that if you look to the energy density of the universe, that you are able to explain 5%. And the rest is dark. I think that's reason enough to do science.
And even that 5% shouldn't be here, according to Hitoshi. Okay, Beata?
Right, I wanted to add, it's also maybe when people think also, at the time when Einstein did his work on general relativity, everybody was very happy with Newtonian mechanics, right? It wasn't that there was anything flawed with it, but we would have never had black holes, we would have never had gravitational waves from it, but this work was done just to try to really get a real understanding of gravity, and he pioneered it, but it wasn't that there was something wrong with Newtonian mechanics as far as one knew. It was describing how the apple falls from this tree, it was describing how the planets revolved, except for Mercury had a bit of a problem. Mm-hmm. But like that tiny little problem sparked a completely new theory, which it's not the theory that gave us black holes, but at least now we understand that there's black holes, we understand there's gravitational waves.
We need it for GPS.
we have GPS, otherwise it wouldn't work. We would all go into the river all the time or wherever instead of on the street. Exactly. So it is not, so it's, yeah, so, well, okay.
Florencia, do you want to add something? Okay. Okay. Then, Jesse, you're the only one who, apart from Florencia, who didn't have a go at that. Is it all been said? Are you got anything you want to add?
Oh, there's many things that I could say. I'm in it for the human curiosity. Let me leave it at that.
Okay, cool. So I think we're at the stage where we wrap up, and I want you all to, Jesse mentioned, was it disciplined, rigorous speculation, yeah? So we talked about what this machine might do. If this the machine that this meeting is about, which is a precision electron-positron collider, which will produce lots and lots of Higgs bosons that will allow us to study that carefully. Will also produce lots of top quarks, produce electroweak events that we can measure the area, the energy region where the Higgs is frozen into the universe very precisely. So this is just between us. You're not going to be quoted, apart from the recording on YouTube and all the millions of people watching it. What do you hope it will really reveal? And what do you think it will reveal? So what's your optimistic hope and what's your realistic estimate? Shall we start with, who wants to start?
Well, I mean, for me, while I completely agree that it's sort of, not good that we only understand 5% of the universe, but for me, the problem that I've been most excited about and most puzzled since the beginning that I learned about it is the problem of flavor, that we have 3 flavors, the electron and the heavy brother, the muon and the tau. And the only particle in the world that actually understands anything about flavor is the Higgs boson. So I'm somehow hoping that by studying it deeply, that we understand why there is flavor in some way.
Cool. Carl, thank you. And do you think that's likely?
I have no idea.
Absolutely. Good experimentalist. Don't bias yourself. Yeah? Okay,
Yeah.
Carl.
I think for me, the clear minimum of this next machine is that we have to understand the nature of this superhero. Yeah, because the Higgs particle is such a strange particle in the standard model. I mean, you learn in your lectures, you have the fermions, the bosons, but you don't have a spin zero. I mean, this is the only spin zero particle in the standard model, sort of isolated. It looks strange. We have to really understand what its nature is. Is it fundamental? Is it composite or whatever? So, and the LHC has done already a lot up to today, but we need to increase the precision of this Higgs boson in order to really come down to its properties and its nature. So that's the minimum which this machine, I think, can deliver. And of course, I hope as well for more. And I'm completely in line with Beate. The area of flavor is right now a very interesting area because we really don't understand this flavor structure, the mixing in the quark sector and so on. And with precision, again, I think that we can get much more insight there. And also you may find surprises that with precision, you detect new effects which are not described in the standard model.
Maybe it's worth saying for non-physicists on watching that by flavor, I think we're talking about the generations of matter and the fact that the everyday particles are lighter than there's a copy of them that's heavier and there's a copy of them that's heavier. And the thing that makes them heavier is the coupling to the Higgs, which is why the Higgs is, as you say, the thing that knows about flavor. Okay, I just thought it's worth filling in some of the language, maybe. Fabiola, are you willing to speculate, or DG's not allowed to speculate?
I can speculate, of course, but I'm afraid that I'm not to go to speculate much beyond what Beate and Carl already said. I think they mentioned already, but the Higgs boson is very special. It has very special features. We call them quantum numbers in physics. It brings a new type of interaction. It's not gauge interaction, it's Yukawa type, so it's a new interaction. But also, if you look at the standard model, all the problems in the standard model are, I mean, in the theory itself, not let alone all the questions that the standard model is not able to answer, but all the problems in the standard model are related to terms where the Higgs boson interaction is involved. So the flavor problems already mentioned, the vacuum stability problem, the problem of the Higgs mass, and so the so-called naturalness or hierarchy. So by studying the Higgs boson in all details, we may hope to address or to make progress in understanding those problems that have a huge impact in our understanding of the universe.
Thanks. Stay with the video, and Jesse, your speculation or your hopes.
Okay, so first speculations and then expectations. So I think that the biggest question that if we had an answer, I could die happy, is what is the nature of dark matter? This is also, it addresses one of the things that Hitoshi said, but also I like the question of dark matter just because it involves physics at so many different scales. It involves potentially the smallest distance scales in the universe, where we have particles that might describe the microscopic nature of dark matter. We have cosmological experiments and the implications of dark matter on cosmology, also on medium scales for the dynamics in the galaxy. And understanding what dark matter is, and maybe colliders will give us some insight into that, would be wonderful. But also dark matter is a problem that requires different types of experimentation. And in fact, colliders are just part of a broad program involving small, medium, and large scale experiments that I think that synergy is something that I'm really excited about. So if we can understand the nature of dark matter in our lifetime, and especially if we could find answers to that, perhaps if dark matter couples to the Higgs boson in some way, that would be absolutely spectacular. In terms of my expectation, I think there is a question that we don't talk about as being a problem with the standard model, but I'm starting to think of it as a problem with the standard model, is that our ability to make predictions in the standard model is both wonderful for certain aspects of it, but there are certain features of the standard model that even though we know the equations, we don't actually know the implications of those equations. And that has to do with the nature of the strong nuclear force. When you're at very high energies in colliders, we can actually make predictions about the strong nuclear force very accurately. But the binding of quarks via the strong nuclear force is something that we don't fully understand either experimentally or theoretically. And I see an interesting potential opportunity to understand confinement, the way that quarks and gluons are bound together, understanding that with collider data, and also with the new generation of calculational strategies. I think that's going to be something really interesting and kind of a guaranteed development. And one of the interesting things about the Higgs boson is that the Higgs boson plays a role in this, since the Higgs has a prominent decay to gluons. And actually that gives us an opportunity to study gluons using a new lens at a Higgs factor. So that's something which it's standard model physics in terms of the equations, but beyond our current understanding of the standard model in terms of its implications.
Cool.
Okay, I think that covered a lot, so I just have to pick which one I like the most. So I think, is it? Yeah,
I think it might be that or me. I don't know.
Okay. No, I think that for me, the one that I will also prefer, if I could have an answer, would be the dark matter. And but what will get me excited is, about Higgs factory is also to see the interplay of the precision in many sectors, and the interplay, and see how everything will come together, and see what cracks in the standard model.
Thank you. Hitoshi, do you want to add it?
Well, I sort of shared my speculations already, but I'm really excited about this possibility that Higgs boson talks to the dark sector. And if the dark matter happens to be in this energy range, it theoretically, the interaction with the Higgs boson is the dominant one. So it's quite natural to think that way. And I'm very hopeful. I'm very excited about the potential opportunity.
Thanks very much, everyone. I said that was the last question. I think we should do that. There was one, I just have to add, there was one that came in while you were all talking, which was, physics is a quantitative science. Is anyone actually going to give a number on anything? I think I'll just point out that about half this meeting is about people trying very hard to do precision calculations to predict exactly what we will try and measure with this machine. Most of them with the standard model, but some of them with their rigorous speculations as well. So that is going on. We maybe haven't covered it in detail, but there are numbers behind a lot of these statements about precision. I think we've probably stressed our panel enough, and maybe the audience too. So we should call it a day now. I'd just like to finish up with a few words, which I should make sure I thank all the right people. That's why I'm doing this. So I'm not going to attempt to summarize the discussion. I hope people watching have got some flavor of the kind of questions. Actually, we ask a lot of the questions that we're asked, the questions we ask ourselves, often less politely in more private fora. I hope at least people have got an idea of the kind of discussions and debate that goes on when we're trying to develop our future and work out what our priorities are. And also for any of the early career younger scientists in the room, I hope you've got some clue how you can join that process effectively and influence it. I would like to then finally just finish with thanking everyone, the audience and the people online who sent questions in. I'd like to thank all the panelists. It's quite stressful sitting up here in front of, even though the chairs are remarkably comfortable, it's very good. But it's still quite hard work sitting in front of an audience and a camera all that time, so thank you very much. Again, thank you to the DPG, the Deutsche Physical-Gesellschaft, and the Quantum Universe Cluster of Excellence here at DAISY, and the DAISY Meeting Service for the technical assistance all the way through. And I think, and since Hitoshi started, Auf Deutsch, I just say, vielen Dank und guten Nacht.